My name is Isaiah, and I'm going to tell you guys about our system Euler. I'll go over how it works really quickly, but I'm going to try to go a little more into how we actually evaluated it and how do you account for anomaly detection and qualify things like speed and precision and stuff like that. So the main thrust of how our Euler works is we view network activity as a temporal graph. A lot of other systems like to look at individual interactions that hosts have on a network and look at the features. Or some people like to just look at the temporal aspect and try to identify anomalies as quick bursts of activity. But we think it's more robust if you look at networks as temporal graphs, so you can analyze how the connections and the structures between entities change as time goes by. So a quick definition of a temporal graph. I assume you all know that a graph is a collection of vertices that have relationships, edges between them. We're using a discrete temporal graph structure, so that's a whole series of graphs that the edges and possibly the nodes are changing over time. And to analyze temporal graphs, we're going to use a temporal link predictor. Now, the way the state-of-the-art does this, in most cases, with discrete graphs anyway, is they have the, I don't have a laser pointer on this, you're just going to have to look at it with your eyes. The individual graph snapshots, the graphs at a certain time, are passed into a graph neural network, usually a graph convolutional network, graph sage, doesn't really matter. Some sort of graph neural network that's going to take the edges and nodes and output a vector for each node representing that node's embedding. And then it's going to take those embeddings and pass that through an RNN, recurrent neural network, that's going to take into account how those embeddings change over time. Then the output of those RNNs is going to go into the next graph neural network so that time and structure are both ingested at the same time for each graph neural network. Now, we've identified that it produces a significant problem, the main problem being that this forces you to process all of these snapshots sequentially, which is often a problem with recurrent neural networks. The biggest chunk of compute time needed is on those graph neural networks because they're making a lot of different random accesses. So following Amdahl's law, if we take all of the graph computes and do them in parallel, we're going to save the most possible time. So we're just going to completely ignore the time part during the graph neural network pass and wait until all the graph neural networks have been have finished running to then run those embeddings through recurrent neural networks. And we'll show that this speeds up the process quite a bit, and it does not affect precision in any meaningful way. So here's our framework. I went over this in a little more detail in my NDSS talk. I'll try to just quickly go over it. If there's questions, I can answer them later. But the idea is that you have one leader machine that's coordinating the actions of several worker machines. The leader machine holds a recurrent neural network, and all the workers hold the graph neural network. It doesn't matter which one you use. We tested, I think, 6 or 9 different configurations of graph neural network and recurrent neural network architectures. But the gist of it is the workers hold the graphs. They compute them through a recurrent neural net or through a graph neural network. Their outputs are sent back to the leader, which runs the topological embeddings through a recurrent neural network to produce the final embeddings that are going to be used to predict whether or not an edge should exist between two nodes. And in this case, an edge means a communication, and nodes are hosts on a network. So the way we do this a little more in depth is we're going to have an encoder function, f, which takes all of the graphs in. As you can see, it produces z, the embeddings of the nodes. And then we have a decoding function, g, which takes the embeddings at some point in time and produces a probability of whether or not an edge should exist between those two nodes, given their embeddings. For most of this, we just use a simple inner product decoder, which means you take the embedding for one node, take the embedding for another node, and the dot product, and then the sigmoid of that is the probability of whether or not there's an edge. We did do some experimentation with that function as well that I'll get into later, but for the most part, inner product worked quite well. For classifying, most of the experiments we use regression metrics. So we're using area under the curve, average precision, and so on. But it's also useful to have an idea of what the true positive rate and false positive rate would be if we were to pick a threshold and then classify certain nodes as malicious or certain edges as anomalous or non-anomalous. So to do that, we hold out a certain set of the training data. It's 5% of the snapshots that we know for sure are benign. We run Euler and calculate the scores for a bunch of edges and a bunch of non-edges, and then according to that little formula right there, that's how we set the threshold. So let's get into the actual experiments that we did. So first, we wanted to make sure that this design actually works, not just as a lateral movement detector in a network, but just in general as a temporal graph as a temporal graph link predictor. So we compared it to 3 different prior works. At the time, I don't think this is true anymore, but at the time, VGRNN was the #1 on paperswithcode.com. EGCN is another really impressive link prediction module, but it's kind of slow and bulky. But EGCN really excels at predicting how a graph is going to look far, far in the future with very little input. And then finally, sort of as an ablation study, we have 3 networks at the bottom under the DynGraph to VEC family. These neural network architectures do not use any sort of graph neural networks. They're using entirely traditional feed-forward neural networks. And these are just combinations of using just feed-forward neural networks, using just recurrent neural networks, or using a feed-forward and a recurrent neural network in conjunction with each other. I don't know if I can go back. Can I go back? Yeah. It's also worth noting that the DynGraph to VEC stuff, that's all reported in the VGRNN paper, so we didn't run those experiments ourselves. We did try to replicate the VGRNN numbers successfully. The EGCN numbers are all our own. We implemented their formula. So the data sets we used are also those that were tested by VGRNN. We used the Facebook data set, the Colab data set, and the Enron 10 data set. If you're not familiar, Facebook is a data set of, I think it's a few thousand users, a few hundred users commenting on each other's walls. So nodes are users, edges are if one user comments on another user's wall. Each snapshot is 1 day long. The Colab dataset is not really something that people traditionally think of as a temporal graph, but it's a citation network of papers, and each snapshot is the papers in a year that have cited each other. This one's kind of interesting because it's only moving forward in time. It almost creates a tree, but there are some cycles in it. And finally, there's the Enron 10 dataset, which are emails between employees at Enron and its final days over the course of 10 weeks, who's emailing whom. And then the tests we did are first dynamic link detection, which is given partial views of each graph. Can we predict whether or not an edge should exist, given what we've seen about a whole bunch of graphs up until time t, but only partially observed graphs? There's also dynamic link prediction, which is given graphs up till time t that are fully observed, can we predict whether an edge will exist between 2 nodes in the next time step? And then finally, dynamic new link prediction, which is sort of the same thing, but we're only looking at edges that are in the next time step that were not in the previous time step, which is just to verify that it is being able to predict temporal patterns of when new edges will appear in time. And the results, I hope you can see that, are a little small, but the results were that Euler either outperformed or performed as well as VGRNN. It outperformed, I think, all the other models, but it performed as well with, it only outperformed VGRNN with statistical significance on, I believe it is on the dynamic link detection methods. And what that means is something that I think I'd really like to see in more machine learning papers in general that I'm going to talk about for a little bit. And that's this whole notion of statistical significance and t-testing. Every single other field of science really uses t-tests, except for machine learning for some reason. And I think this is kind of a big problem. What this means is that because these models are very often stochastic and they're going to produce slightly different outputs, it's really important to take the standard error between your models. Surely everyone is averaging 10 independent runs to give these output numbers. But then everyone always gives these little plus or minus that error margin, but no one actually uses it. The real reason that exists is so you can do hypothesis testing. There's a little formula down here, and if it comes to a number less than 2.228, it means that the p-value, the likelihood that those two distributions are deviating, that means that the value A in that formula, in this case Euler, is outperforming it with statistical significance. It's really useful, I think, for a lot of reasons. If you guys are doing machine learning papers, it's really useful to make your paper look good because you can prove that there's a lot of ties even when it looks like there may not be. Or you can prove that your model is better even when it's unclear because the error bounds are smaller. So just something to think about. Another important thing that we tested with these other models is the actual speed. And this was on a much bigger data set, the one that I'll be talking about in just a second, because on the small data sets, the speeds were more or less the same. There were only a few thousand edges in those graphs. But on the bigger data sets, Euler, which is the lightest bar on the furthest to the right, always performs much better in terms of speed. It runs about double the speed of VGRNN, which is the second best model tested. And this is something that we're not really sure how to account for on papers with code or like any of those like ranking websites. If our model is equivalent to VGRNN in terms of precision, but it's twice the speed, it seems like we can say it's better, but I'll leave that for the peers to review, as it were. Finally, once we've decided that it worked efficiently on smaller data sets, we wanted to test Euler on real-world data sets and see how it does at detecting lateral movement. So the important thing here is that if you view networks as a graph, and if an edge occurs between two nodes in a communication network, but if we have a well-trained link predictor and it thinks that the likelihood of that edge existing is low, we're going to assign it as an anomalous connection. And anomalous connections very often correlate with lateral movement in a network. If two computers are authenticating with each other that don't normally talk to each other, that could mean that an advanced persistent threat is trying to get through your network, trying to get to a more important computer that it's on, and so forth. So that's the threat model we're working on here. The first data set we tested, and I believe the only one in the actual paper, is the Landlord Data Set, which consists of 58 days of log files in a real-world system, where there's sporadic attacks, sporadic malware campaigns on that system. The red log for this dataset identifies 750 authorization events that were, quote, evolved in compromise. And I put quotes around that because it's not very clear if they were just, that's when they were compromised and then they continued spreading malware, or what. The red log is really just a list of events in this, I think it's 45 billion line long file. And we're going to, in just a little bit, we're going to see how having more informative red team logs is useful, not just for training these malware detectors, but I think also for evaluating them. The nodes were users, computers, and systems in the network, and edges are authorizations between those entities weighted according to their frequency in each time window. And we conducted 9 different tests, we conducted tests on 9 different configurations of Euler, as well as 4 prior works. We tested 3 different encoding or graph encoding modules. So we tested graph convolutional network, graph sage, and graph attention network, which are all very commonly used graph neural networks. We tested 3 RNNs, or rather 2 RNNs, and as an ablation study, no RNN. So we tested GRUs, LSTMs, and none, which was just taking the output of each graph neural network and using that as the embedding without looking at time whatsoever. And finally, we compared it to 4 prior works, GLLV and GLGV are it's one from one paper. It's two different ways of looking at a network as one large static graph that doesn't change over time, and using node to vec, which is similar to word to vec, if you're familiar, to produce node embeddings. UA is unrecognized authorization. That just means for the first, prior to the red team attacks, looking at every single authorization event that happened, and any new authorization that wasn't tracked, we're going to mark that as anomalous. That, as it turns out, is not very effective. And finally, we also tested VGRNN, which is the state-of-the-art link predictor. You'll notice that we're not testing evolving GCN, even though it's also state-of-the-art, and that's because in all of the tests, it is far, far too slow. It just does not, it is not scalable to this size of the data. So here are our results. Again, I'm sorry the table's kind of small, but what you can see in the results is that the area under the curve and the average precision are very, very high for graph convolutional network and graph SAGE. They're not so good for graph attention network. The other GLLV and GLGV and UA, those are all rules-based things, so those do not really have scores, so we couldn't report the area under the curve or average precision. So we had to rely on false positive rate and true positive rate. And this is where I think it's important to, I want to talk more about this with the difference between regression metrics and classification metrics. Because you can see on, I think it's for link prediction, VGRNN gets the lowest false positive rate of anything. That might be link detection. But you'll notice that its true positive rate's like 75, something like that. But then you look at Euler, which has a about as low false positive rate. It's like 0.5%, but its true positive rate is like way, way higher. So what that shows is if we just set the threshold to be like a little tiny bit lower, that Euler would have been equivalent to VGRNN. And it's stuff like that where I think it's really hard to truly decide which of these models is better at it. That's why I like looking at the regression metrics, because you can always change where you're going to set that threshold for your cutoff, but it's very hard to change the actual quality of the edge predictions. So that's why I think it's more useful to look at average precision, area under the curve. But you will notice average precision is still rather high or rather low. It's I think it's 0.08 in the best case, which is not very good. So what we need to do is look at a more detailed data set and figure out if it's our problem or if it's the labeling that's the problem. And when we look at this data set, OPTC, or transparent computing, as I've heard some people call it, which is much more detailed, it's a much larger data set as well. We get much better results. This data set consists of fewer nodes. It's only, it's about 1,000, I think, but much more events, many more events. And we're doing the same thing. We're constructing a temporal graph with edges are flow starts between two entities in the network. Again, they're weighted in the same way as the Landlord data set. And no features, just like in the Landlord data set, we're just using one hot IDs. And here we're manually labeling edges, sort of. We're looking at the red team log, and if a source or a destination IP was seen in an attack that's taken place, then that edge is marked as anomalous. Similarly, if the process ID was in the red team event and it happened after the attack started, or it was logged to have started, that we mark it as anomalous as well. We have much more fine-tuned ability to label edges here rather than just being given a red log. And when we can do that, when we can more adequately label edges and know exactly what we're talking about, you can see the precision goes way, way up. It's like in the 90s now. And we didn't report this in the paper, the NDSS paper. We just didn't have space for it. But this, when you have more fine-tuned control over the data and know exactly what's going into it, these results get a lot better. Another thing to take into account is that there were fewer hosts, so instead of using inner product decoding, we could use a different kind of decoder. We used a softmax, like just an additional layer of a neural network, and that really boosted the scores like quite significantly. So I think it's safe to say that with all of these things added on top of Euler, it might even be usable as a real-life intrusion detection system. But again, that's for other people to decide. I'm just here to report the numbers. So in conclusion, Euler accomplished the following. It was consistently as powerful or better than prior work. It parallelized temporal link prediction. It's the first use, as far as we know, of a graph temporal link prediction for an intrusion detection system. And it achieved very good scores on the transparent computing data set and better scores than the prior work on Lateral. So here are my little discussion topics that I was trying to bring up throughout, or if you guys have any other questions, please let me know.